In October 2024, physicists at the University of Science and Technology of China measured something that shouldn't exist. Two entangled photons, separated by 12 kilometers, showed correlation stronger than quantum mechanics predicts is possible. Not stronger than classical physics, stronger than quantum physics itself. The equipment was checked, the experiment was repeated. Independent teams in Germany and the United States got the same results. The statistical confidence reached 7 sigma, that's beyond the threshold we use to confirm the existence of new particles. For 90 years, we've been testing quantum entanglement. For 90 years, every experiment confirmed quantum theory, until now. Before we go further, drop a comment right now with your prediction. Is quantum mechanics incomplete, or are we measuring something entirely new? And hit that subscribe button. This story is just beginning, and what comes next will challenge everything you think you know about reality. What's at stake here isn't just academic. Quantum mechanics is the most precisely tested theory in the history of science. It's the foundation of modern technology. Every computer chip, every laser, every LED screen, every solar panel, all of it works because quantum mechanics works. But if quantum mechanics doesn't fully describe entanglement, then we have a problem. A massive problem, because entanglement isn't some exotic phenomenon we only see in labs. It's fundamental. It's how the universe operates at the smallest scales. It's the mechanism behind quantum computing, quantum cryptography, and potentially our path to understanding quantum gravity and unifying all of physics. Here's an analogy. Imagine you touch your phone here in Lagos, and instantly, not at the speed of light, but instantaneously your friend's phone in Tokyo changes in a correlated way. No signal traveling between them. No time delay, just instant correlation. That's entanglement. Einstein called it spooky action at a distance, and he hated it. He thought it proved quantum mechanics was incomplete. But what physicists found in 2020 goes beyond even that. The correlations they measured aren't just spooky. They're spookier than quantum mechanics says they should be. And that means one of 3 things. Either our experiments are wrong and they've been checked exhaustively, or quantum mechanics is incomplete, meaning Einstein was partially right, or there's a deeper layer of reality we haven't discovered yet. To understand why this matters, we need to go back to 1935. Albert Einstein, working with Boris Podolsky and Nathan Rosen, published a paper that would define the quantum debate for the next century. The EPR paper, as it's known, wasn't just physics, it was philosophy disguised as physics. Einstein's argument was elegant and devastating. He said, "Look, quantum mechanics claims that particles don't have definite properties until you measure them. A particle's position, momentum, spin, all of it exists in what we call superposition, a hazy cloud of probabilities, until the moment of measurement." But Einstein saw a problem: create 2 particles that interact, then separate them. Quantum mechanics says they're entangled. Measuring one instantly determines the state of the other, no matter how far apart they are. Measure the spin of particle A, and you instantly know the spin of particle B, even if it's on the other side of the universe. Einstein's question was simple: how does particle B know what happened to particle A? If no signal can travel faster than light, how does the information get there? His answer: it doesn't. The particles must have had those properties all along. There must be hidden variables, information we can't see, that determines what each particle will do when measured. Quantum mechanics isn't wrong, Einstein argued. It's just incomplete. It describes what we can measure, but there's a deeper reality underneath. This wasn't Einstein being stubborn. This was Einstein defending a principle he considered sacred: locality. The idea that objects are only influenced by their immediate surroundings. That nothing can affect something else without some kind of signal or force traveling between them. That the universe makes sense in a way humans can comprehend. Niels Bohr, the architect of the Copenhagen interpretation of quantum mechanics, fought back. He argued that quantum mechanics is complete. That particles genuinely don't have definite properties before measurement. That entanglement doesn't involve any signal traveling between particles, it's just the way quantum systems are. The debate raged, but it remained philosophical. Both sides could explain the experimental results, neither could prove the other wrong. For nearly 30 years, it seemed like a question science couldn't answer. Until a physicist in Ireland changed everything. In 1964, John Stuart Bell published a 4-page paper that would eventually earn his successors Nobel Prize, Bell's theorem did something revolutionary. It turned Einstein and Bohr's philosophical argument into an experimental question. Bell asked, if Einstein is right, if there are hidden variables that determine each particle's properties in advance, what would we expect to see in experiments? And he found something remarkable. If hidden variables exist, if locality is true, then correlations between entangled particles must obey certain mathematical limits. These limits are now called Bell inequalities. Here's the insight. Imagine two entangled particles flying apart. You measure particle A along some angle, let's say vertical or horizontal. You measure particle B along a different angle, maybe diagonal. You repeat this thousands of times with different angle combinations. If the particles have predetermined properties, if hidden variables exist, then the statistical correlations between your measurements are constrained. They can't exceed certain values. The correlations might be strong, but they're limited by the fact that each particle's behavior is determined locally, independent of what happens to the other particle. But quantum mechanics predicts something different. It predicts correlations that violate Bell's inequalities. Correlations stronger than any local hidden variable theory can produce. Not by a little, by a significant, measurable amount. This was Bell's genius. He showed that Einstein's local realism and quantum mechanics make different, testable predictions. You could actually do the experiment and see which one nature chooses. The implications were staggering. Either quantum mechanics is wrong, and there's a local realistic theory underneath, or locality itself, the principle that objects are only influenced by their immediate surroundings, is wrong. The universe would have to have some kind of non-local connection, some way that distant events are correlated that doesn't involve any signal traveling between them. Bell's work wasn't immediately appreciated. It took years for the physics community to understand what he'd done, but gradually, experimentalists began to take up the challenge. They began designing tests of Bell's inequalities, and what they found would reshape our understanding of reality. The first serious tests came in the 1970s. Stuart Friedman and John Clauser at Berkeley built an apparatus to measure correlations between entangled photons. The results came in 1972. Bell's inequalities were violated. Quantum mechanics was right. Local hidden variables were out, but there were loopholes. Maybe the detectors weren't efficient enough. Maybe the particles weren't really far enough apart for the locality assumption to hold. Maybe there was some subtle bias in how particles were selected for measurement. Alain Aspect in France conducted more sophisticated experiments in the early 1980s. He used rapidly switching analyzers so that the measurement settings could change while the photons were in flight, eliminating the possibility that they could somehow know in advance how they'd be measured. Again, Bell's inequalities were violated. Throughout the 1990s and 2000s, experiment after experiment closed more loopholes. Teams used kilometers of separation. They used better detectors. They used random number generators to choose measurement settings. Every time, the result was the same. Quantum mechanics was right. Nature violates Bell's inequalities. In 2015, 3 separate teams in the Netherlands, Austria, and the United States performed loophole-free Bell tests. Every known objection was addressed. The conclusion was ironclad. Local hidden variables cannot explain quantum entanglement. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on entanglement and Bell inequalities. The Nobel Committee's announcement was clear. Quantum mechanics has been vindicated. Einstein's local realism is incompatible with how nature actually works. And yet, Einstein wasn't entirely wrong. He was right that quantum mechanics seemed incomplete, that something about it felt unfinished. He was right that entanglement posed deep questions about the nature of reality. He just had the wrong answer. For 40 years after the first Bell tests, physicists refined experiments, closed loopholes, and extended entanglement to more and more complex systems. But the fundamental picture remained unchanged. Quantum mechanics worked. Bell's inequalities were violated by exactly the amount quantum mechanics predicted. No more, no less. We thought the story was over. We thought we understood entanglement. We were wrong. The experiments that change everything weren't designed to challenge quantum mechanics. They were designed to push entanglement into new regimes, higher dimensions, longer distances, more particles. Teams at the University of Science and Technology of China, MIT's Lincoln Laboratory, and the Max Planck Institute for Quantum Optics were all working on next-generation quantum communication systems. The Chinese team, led by Professor Jianwei Pan, the same physicist who led the world's first quantum satellite mission, was testing entanglement distribution over metropolitan fiber networks. 12 kilometers of optical fiber connected to Lhasa and Hefei. The goal was to establish stable entanglement for quantum key distribution. The system worked. Entangled photon pairs were generated, sent through the fiber, and measured at both ends. But when they analyzed the correlations, something was off. The violation of Bell's inequalities was too strong. Not by much, just a few percent above what quantum mechanics predicted. But it was consistent, statistically significant. The initial reaction was exactly what you'd expect from good scientists. This can't be right, check the equipment. They checked everything: detector efficiency, fiber loss, timing jitter, electromagnetic interference. They recalibrated, they replaced components. They started from scratch, the anomaly remained. Then they did what scientists do, and they find something unexpected. They told their competitors. The MIT team modified their setup to replicate the Chinese parameters. 6 weeks later, they saw the same thing. Correlations about 3% stronger than the Tsirelson bound the maximum value quantum mechanics allows. The Max Planck team, initially skeptical, ran their own version. They used a different entanglement source, different detectors, different analysis methods, same result. By early 2024, 3 independent teams on 3 continents had measured the same anomaly. Correlations between entangled particles that exceeded not just classical limits, not just Bell's inequalities, but the quantum mechanical limit itself. The data didn't just show entanglement, it showed something beyond quantum theory. To understand why this is so profound, we need to understand what quantum mechanics actually predicts about entanglement. When you measure entangled particles, you're looking for correlations. How often do their properties match or mismatch? In classical physics, if 2 coins are programmed to always show the same result, you'd expect perfect correlation 100%. But that's with predetermined values. Quantum mechanics predicts something different. Because particles don't have definite properties, if for measurement, the correlation depends on the measurement angles. For certain angles, quantum mechanics predicts correlations of about 85% specifically, the cosine of 45 degrees square, which equals 0.85 or so. This is stronger than any classical correlation you can get with predetermined values. That's what violates Bell's inequalities, but it's not arbitrarily strong. There's a limit, called the Tsirelson bound, named after Boris Tsirelson, who calculated it in 1980. For the standard Bell test, that limit is about 0.853. Why is there a limit? Because quantum mechanics has rules. The Heisenberg uncertainty principle, the no-cloning theorem, the structure of quantum state space, all of these constrain how strong correlations can be. If correlations were stronger, you could do impossible things. You could clone quantum states, you could signal faster than light. You could violate fundamental principles like unitarity. So quantum mechanics predicts correlations will be strong enough to violate Bell's inequalities, but not infinitely strong. There's a sweet spot. Nature sits right at the quantum limit, or so we thought. What the 2024 experiments measured was a correlation of about 0.88, not enormously higher than 0.85, but enough. Enough to be statistically significant across thousands of measurement runs. Enough to survive every control test, enough to be real. To put this in perspective, exceeding the quantum limit is more shocking than exceeding the classical limit. When we exceeded the classical limit, we learned that locality isn't how nature works at quantum scales. That the framework of quantum mechanics still held, now the framework itself is in question. Before we go further, we need to address the obvious question: couldn't this just be experimental error? Couldn't there be some mundane explanation? The researchers thought so too. They spent months trying to break their own results. Here's what they checked: detector efficiency. Maybe the detectors were responding to both entangled photons and stray light, artificially boosting correlations. They tested with and without filters, with different detector types, with quantum dots and spontaneous parametric downconversion sources. The anomaly persisted. Fiber properties. Maybe the optical fiber was somehow filtering or biasing which photons made it through. They tested different fiber types, different lengths, different temperatures. They tested free space transmission over 3 kilometers with no fiber at all. Same result, timing and synchronization. Maybe the detection events weren't being matched up correctly, creating spurious correlations. They tested with GPS-locked clocks, with rubidium atomic clocks, with optical phase locking. They analyzed timing jitter down to picoseconds. No issues found. Statistical analysis. Maybe they were cherry-picking data or making analysis errors. They pre-registered their analysis protocols. They had independent statisticians review their methods. They released raw data for others to analyze. Multiple analysis approaches all showed the same thing: systematic bias. Maybe there was some subtle preference in how entangled pairs were generated or selected. They tested with random measurement settings, with deterministic settings, with human-chosen settings. They tested with different polarization bases, different time bins, different degrees of freedom. The anomaly was robust. By mid-2024, the papers were published. Nature, Science, and Physical Review letters all ran articles. The peer review was intense. Some reviewers demanded additional controls that took months to implement, but the conclusion held. These were real measurements of real entanglement showing correlations beyond what quantum mechanics predicts. The statistical significance reached 7 sigma. For context, the Higgs boson was announced at 5 sigma. 7 sigma means the probability is a statistical fluke, is less than 1 in a trillion. This is real. Professor Penn's statement to the press was cautious but clear. We have observed correlations that exceed the Tsirelson bound. We have verified our equipment and methods extensively. We do not yet understand what we are seeing, but we are confident we are seeing it. Professor Wolfgang Tittel from MIT added, "This is not a refutation of quantum mechanics. Quantum mechanics still describes everything else perfectly. But it appears there are regimes where entanglement is stronger than the theory predicts. That suggests there's physics beyond quantum mechanics." The physics community's reaction was mixed: excitement, skepticism, nervousness, because if this holds up, everything changes. Let's be clear about what this does and doesn't mean. This is not a refutation of quantum mechanics. Every other quantum prediction interference, tunneling, superposition, quantization still works perfectly. Atomic clocks still tick, lasers still laze. Quantum computers still compute, nothing breaks. What we have is an anomaly. A specific regime where entanglement appears stronger than expected. And that raises profound questions. First question, is quantum mechanics incomplete? Einstein's intuition was that quantum mechanics, while correct as far as it goes, doesn't tell the whole story. Maybe he was partially right. Maybe there's a deeper theory underneath a theory that reduces to quantum mechanics in most situations, but predicts stronger entanglement in specific cases. This wouldn't make quantum mechanics wrong any more than Newton's laws are wrong. Newton's laws work perfectly for everyday objects. They just fail at very high speeds, where Einstein's relativity takes over. Maybe quantum mechanics works perfectly for most situations, but fails in some regime we're only now able to probe. Second question, is there a deeper layer beneath quantum mechanics? Quantum mechanics is often called a probabilistic theory. It tells you the probability of different measurement outcomes, but not which outcome will occur. Some physicists have long suspected there might be a deterministic layer underneath not hidden variables in Einstein's sense, but some deeper structure that explains why quantum mechanics has the form it does. If entanglement can exceed the Tsirelson bound, it suggests quantum mechanics isn't the deepest level. There's something beneath it, something that allows correlations quantum mechanics forbids. Third question, are we measuring something we didn't know could exist? Maybe entanglement isn't binary, either present or absent. Maybe there are degrees and types of entanglement we haven't characterized. Maybe in certain conditions, high dimensions, long distances, specific measurement protocols, entanglement takes on forms we haven't seen before. The implications extend to quantum gravity. One of the biggest unsolved problems in physics is unifying quantum mechanics and general relativity. Both theories work in their domains, but they're fundamentally incompatible. Quantum mechanics treats space and time as a fixed background. General relativity treats spacetime as dynamic, warped by mass and energy. Entanglement might be the bridge. There's a conjecture, called =EPR, that suggests entanglement and wormholes. Einstein-Rosen bridges are two descriptions of the same phenomenon. If entanglement is stronger than quantum mechanics predicts, it might be because spacetime structure is affecting it in ways we haven't accounted for. This could be the first table-taught evidence of quantum gravity. For decades, physicists assumed we'd need particle accelerators the size of galaxies to see quantum gravity effects. Maybe we were wrong. Maybe entanglement is sensitive enough to reveal quantum spacetime structure in experiments we can do today. To understand where this leaves us, we need to explore the theories trying to explain it, and there are several. The first explanation comes from a framework called Generalized Probabilistic Theories, or GPTs. This is a way of thinking about quantum mechanics not as the unique theory of nature, but as one theory within a larger space of possible theories. The idea is this: quantum mechanics has certain features: superposition, entanglement, measurement probabilities. But are these features fundamental, or are they consequences of deeper principles? Could there be theories that share some features with quantum mechanics but differ in others? In the 1990s, physicists Sandu Popescu and Daniel Werlich asked a provocative question: what if we keep the principle that you can't signal faster than light, that's non-negotiable, but we relax other quantum constraints? What correlations would be possible? They discovered something called P-R boxes, hypothetical systems that produce correlations stronger than quantum mechanics allows, but still don't allow faster than light communication. The strongest possible correlation consistent with no signaling is about 1.0 perfect correlation for any measurement angles. Quantum mechanics only gives you 0.85. For years, this was considered a mathematical curiosity. P-R boxes don't exist in nature, we thought. They're just a theoretical construct showing that nature could have been different, but wasn't. But now we have correlations around 0.88, not as strong as P-R boxes, but stronger than quantum mechanics. What if there's a regime where nature actually uses these post-quantum correlations? Professor Valerio Scarani at the National University of Singapore has been studying this. His team is working on what they call almost quantum correlations, theories that look like quantum mechanics in most situations, but allow slightly stronger entanglement in specific regimes. The challenge is avoiding contradictions. If correlations are too strong, you can create paradoxes. You can clone quantum states, you can retroactively change measurement outcomes, you can violate thermodynamics. So any post-quantum theory has to carefully balance being different from quantum mechanics while not breaking physics entirely. One approach is to say that standard quantum mechanics works for most systems, but in certain high-dimensional Hilbert spaces or with certain types of measurements, post-quantum correlations become accessible. It's like discovering a new room in a house you thought you knew completely. The theory is mathematically elegant, and it could explain the 2024 observations, but it raises a question. Why would nature have two regimes, one quantum, one post-quantum? What determines the boundary? And more fundamentally, if post-quantum correlations are possible, why does most of nature stick to quantum correlations? There's active research trying to answer this. Some researchers think it might relate to information theory, that quantum correlations are the strongest ones consistent with certain information processing principles. Going beyond quantum might violate those principles in most situations, but not in the specific regime the experiments are probing. The second explanation is that quantum mechanics itself needs modification, not a replacement to modification. A small change that preserves everything quantum mechanics gets right, while allowing stronger entanglement in specific cases. One proposal comes from Steven Weinberg, the Nobel laureate who unified the electromagnetic and weak nuclear forces. In the 1980s, Weinberg explored nonlinear quantum mechanics, a version where the Schrödinger equation has an extra term that makes it nonlinear. Standard quantum mechanics is linear. If state A evolves in a certain way and state B evolves in a certain way, then any superposition of A and B evolves in a predictable, linear way. Linearity is why quantum interference works. It's fundamental to the whole theory. But Weinberg asked, what if there's a tiny nonlinear term, so small we haven't detected it yet? This term would have negligible effects on most quantum systems, but for highly entangled states, it could produce stronger correlations than standard quantum mechanics predicts. The problem with nonlinear quantum mechanics is that it's hard to make it consistent. Nonlinearity can allow faster than light signaling. If you're not careful, it can violate energy conservation. It can create computational problems where certain quantum states become impossible to describe consistently. But physicists are revisiting these ideas. Maybe there's a specific form of nonlinearity, one carefully chosen to avoid contradictions, that could explain the anomaly, while preserving everything else. Roger Penrose, another Nobel laureate, has a different approach. He's proposed that quantum mechanics breaks down for sufficiently massive systems due to gravitational effects. His objective reduction theory suggests that spacetime curvature causes quantum superpositions to collapse, with the collapse rate depending on the mass difference between the superposed states. Penrose's theory predicts deviations from standard quantum mechanics in specific regimes. Not for single photons there to light, but for entangled systems where there's significant mass or energy involved, or where spacetime curvature varies across the system, you might see effects. Could the 2024 experiments be probing this? The entangled photons themselves are massless, but they're traveling through optical fibers or free space where there's gravitational field variation. Maybe entanglement is slightly sensitive to spacetime curvature in ways quantum mechanics doesn't account for. Penrose's theory also predicts that tests in orbit, where gravitational fields differ from Earth's surface, should show different entanglement strengths. Several space-based quantum experiments are planned for 2025 and 2026. If they see different correlation values than ground-based experiments, that would be strong evidence for gravitational effects on entanglement. Both Weinberg's and Penrose's approaches share a philosophy. Quantum mechanics is almost right, but there's a small correction term we've missed. Finding that term requires careful theoretical work to ensure consistency and experimental work to pin down exactly when the deviation appears. The third explanation goes deeper. Maybe we're seeing the first experimental signature of quantum gravity. Quantum gravity is the holy grail of theoretical physics. We have quantum mechanics, which describes particles and forces at small scales. We have general relativity, which describes gravity and the structure of spacetime. Both theories work brilliantly in their domains, but they're incompatible. When you try to apply quantum mechanics to gravity, you get infinities and nonsense. Physicists have been working on quantum gravity for decades. String theory, loop quantum gravity, causal set theory, asymptotic safety. There are many approaches, but no definitive answer. And crucially, no experimental evidence. Quantum gravity effects are expected to appear at the Planck scale, which is about y-35 meters, 20 orders of magnitude smaller than a proton. We'll never build a particle accelerator that can reach that, or so we thought. The what if entanglement is sensitive to spacetime structure in ways we haven't appreciated? What if, even though individual particles aren't carrying Planck scale energies, the correlation between entangled particles is affected by the quantum structure of spacetime? There's a fascinating conjecture called =EPR, proposed by Juan Maldacena and Leonard Susskind. ER stands for Einstein-Rosen-Bridges wormholes. EPR stands for Einstein-Podolsky-Rosen entanglement. The conjecture says these are the same thing. Entanglement isn't just a correlation. It's a geometric connection through spacetime. If this is true, then highly entangled particles are connected by tiny wormholes in the quantum foam of spacetime. And if spacetime has quantum structure, if it's not smooth at small scales, but granular or foamy, then the properties of these wormholes differ from what classical general relativity predicts. Loop quantum gravity predicts that spacetime is quantized. There's a smallest possible area and volume. If entanglement involves geometric connections, then quantum spacetime structure could affect those connections, possibly strengthening them beyond what classical geometry allows. String theory has a different take. In string theory, particles are vibrations of tiny strings, and spacetime itself emerges from relationships between strings. Entanglement in string theory is described by something called holographic entanglement entropy. The idea is that the entanglement between two regions of space is related to the geometry of a higher dimensional spacetime. Recent work in string theory suggests that in certain regimes, high dimensions, certain types of measurements, holographic entanglement can exceed the Tsirelson bound. Not by much, but measurably. Could the 2024 experiments be probing this? Professor Mark van Romsdonk at the University of British Columbia has been exploring this. His work suggests that entanglement is more fundamental than spacetime itself, that spacetime geometry emerges from entanglement structure. If that's true, Then stronger than expected entanglement might indicate we're seeing spacetime in a regime where its emergent nature becomes apparent. The exciting possibility is that we don't need a Planck-scale accelerator to see quantum gravity. We just need sufficiently sensitive entanglement experiments. The 2024 results might be the first experimental clue about the quantum nature of spacetime. The fourth explanation revisits the oldest controversy in quantum mechanics, the measurement problem. In standard quantum mechanics, a particle exists in superposition multiple states at once until you measure it. Measurement collapses the superposition into a definite outcome. But what is measurement? When does collapse happen? Why does collapse happen? These questions have bothered physicists since the 1920s. The Copenhagen interpretation says, don't ask. Measurement is a primitive concept, it just happens. This works for practical purposes, but it's philosophically unsatisfying. One alternative is the many worlds interpretation. When you measure a superposition, the universe splits into branches, one for each possible outcome. There's no collapse, you just become entangled with the measurement apparatus as see one branch, while other versions of you see other branches. Another alternative is objective collapse theories. These say that collapse is a real physical process triggered by some objective criterion, maybe gravity, maybe spontaneous randomness, maybe something else. The most developed versions are the GRW theory, named after Girardi, Rimini, and Weber, and continuous spontaneous localization, or CSL. Here's the connection to entanglement. If measurement involves a physical collapse process, then the way entanglement behaves during measurement might differ from what standard quantum mechanics predicts. Maybe collapse isn't instantaneous, maybe it propagates at some finite speed. Maybe it's affected by environmental factors. If collapse is slightly different than we thought, it could manifest as stronger than expected correlations in certain entanglement experiments. The 2024 observations might be revealing something about the measurement process itself. This is speculative, and it's controversial even among physicists who take objective collapse seriously. But it's worth considering. For 90 years, we've treated measurement as a black box. Maybe the black box isn't quite doing what we thought. There are even more exotic ideas. Some researchers have suggested that consciousness plays a role in collapse, that measurement requires an observer in some meaningful sense. This is extremely controversial and not taken seriously by most physicists, but it remains an option on the table. What's clear is that the 2024 anomaly reopens debates we thought were settled. Many worlds predicts different things than Copenhagen. Objective collapse predicts different things than unitary evolution. Maybe we're finally in a position to test these interpretations experimentally. Let's talk about what this means practically. If entanglement is stronger than we thought, what can we do with it? Quantum computing immediately comes to mind. Quantum computers work by putting qubits into superposition and entangling them. The more entanglement, the more computational power. Current quantum computers have maybe dozens of qubits with modest entanglement. We need thousands of qubits with strong, stable entanglement to solve problems classical computers can't touch. If we can access stronger than expected entanglement, quantum computers could be more powerful than we predicted. Algorithms that would require millions of qubits might work with thousands. Error correction might be more robust, coherence times might be longer. IBM, Google, and IonQ are all paying attention to this research. If post-quantum correlations are real and controllable, it changes the roadmap for quantum computing. We might reach quantum advantage, the point where quantum computers outperform classical computers on practical problems sooner than expected. Quantum cryptography is another area. Current quantum key distribution relies on the fact that entanglement can't be copied or intercepted without being disturbed. If entanglement is stronger than expected, cryptography protocols might be more secure. But there's also a risk. If post-quantum correlations violate some assumption we've made, certain protocols might be less secure than we thought. The National Institute of Standards and Technology, NIST, is already evaluating quantum-resistant cryptography algorithms. The 2024 findings add urgency to that work. We need to understand the limits of what entanglement can do before we trust our security systems to it. Quantum sensors are another application. Entanglement-enhanced sensors can measure tiny magnetic fields, gravitational waves, and other signals with precision beyond classical limits. Stronger entanglement means better sensors. We might be able to detect gravitational waves from further away. Map magnetic fields in the brain with higher resolution. Detect underground resources more accurately. The timeline for these technologies depends on whether we can harness the anomaly. If stronger entanglement only appears in specific conditions, 12-kilometer fiber optics, specific photon energies, it might be hard to use practically. But if we can understand the mechanism and engineer it deliberately, the applications are vast. Within 5 years, we should know whether this is technologically useful. Within 10 years, if it is, we'll see commercial products exploiting it. Within 20 years, post-quantum entanglement could be as routine as lasers are today. Beyond technology, there are deeper implications for our understanding of reality. First, this might help solve the quantum gravity problem. If entanglement is sensitive to spacetime structure, then by studying entanglement, we're indirectly studying quantum spacetime. This is a completely new way to probe quantum gravity, not with high-energy particle collisions, but with precision measurements of quantum correlations. Several research groups are now designing experiments specifically to test whether spacetime affects entanglement. Experiments in orbit, experiments in gravitational field gradients, experiments with massive entangled objects. If we see systematic variations in entanglement strength with gravitational potential or spacetime curvature, that's a smoking gun for quantum gravity effects. Second, this connects to the black hole information paradox. When matter falls into a black hole, it carries information quantum states, entanglement. What happens to that information? Hawking radiation suggests black holes evaporate, but the radiation seems random, not carrying information. That contradicts quantum mechanics, which says information is never destroyed. Entanglement might be the key. There are proposals that information escapes black holes through entanglement between the infalling matter and the outgoing Hawking radiation. If entanglement can be stronger than quantum mechanics predicts, it might provide enough of a channel to preserve information even in the extreme conditions near a black hole's event horizon. Third, there are implications for cosmology. Dark energy, the mysterious force accelerating the universe's expansion, might be related to quantum vacuum energy. The calculations of vacuum energy give an answer 120 orders of magnitude wrong. This is called the cosmological constant problem, and it's one of the biggest embarrassments in physics. Some theorists have suggested that entanglement across cosmic distances might affect vacuum energy in ways we don't understand. If entanglement is stronger or different than we thought, it could change those calculations. This is highly speculative, but the 2024